J. Thomson, a pioneering British physicist, is best remembered for one of the most revolutionary discoveries in the history of science, the identification of the electron. Born on December 18, 1856, in Cheetham Hill, a suburb of Manchester, England, Joseph John Thomson entered the world during a time of rapid industrial and scientific advancement. His early life was shaped by a strong inclination toward the sciences, particularly physics and mathematics. His father, a bookseller, encouraged young Joseph's curiosity, but died when the boy was only 16, leaving a profound impact on his formative years. Despite this loss, Thomson's intellectual promise remained evident, and he was admitted to Owens College, Manchester, at the age of 14, an impressive achievement by any standard. After completing his initial studies, he moved on to Trinity College, Cambridge, where he would spend most of his academic life. It was at Cambridge that his true scientific journey began, marked by meticulous study and unwavering dedication. He eventually became a Fellow of Trinity College and, in 1884, was appointed as the Cavendish Professor of Experimental Physics. This role placed him at the helm of the renowned Cavendish Laboratory, a center for groundbreaking research. At the time of his appointment, he was only 28 years old, making him one of the youngest scientists to hold the position. It was in this laboratory that Thomson would embark on the experiments that would change the understanding of atomic structure forever. In 1897, through a series of experiments using cathode ray tubes, Thomson discovered that atoms contained smaller, negatively charged particles, what we now know as electrons. Prior to this, the atom was thought to be the smallest, indivisible unit of matter. Thomson's experiments demonstrated that these cathode rays were composed of tiny particles, much smaller than atoms and possessing a negative electric charge. This was a monumental breakthrough because it indicated that atoms were not the fundamental units of matter as previously believed. Instead, they were made up of even more elementary components. This challenged centuries of scientific thought and opened the door to a new field of atomic physics. Thomson proposed a model of the atom that came to be known as the plum pudding model. In this conceptualization, the atom was envisioned as a sphere of positive charge, in which negatively charged electrons were embedded, like raisins in a pudding. Though later refined and eventually replaced by more accurate atomic models, Thomson's theory was a critical stepping stone in the development of modern atomic theory. His work laid the foundation for future scientists such as Ernest Rutherford, Niels Bohr, and others, who would continue to unravel the complexities of atomic structure. In addition to his groundbreaking work on the electron, Thomson made significant contributions to other areas of physics. He conducted important research in electromagnetism, the behavior of gases, and the conduction of electricity through ionized air. His research often intersected with the technological innovations of the day, including the development of early vacuum tubes and radio waves. Thomson was also a dedicated and influential teacher, mentoring numerous students who would go on to make substantial contributions to science themselves. Notably, among his students was Ernest Rutherford, who would later challenge and build upon his atomic model. Thomson's contributions to science were widely recognized during his lifetime. In 1906, he was awarded the Nobel Prize in Physics in recognition of the great merits of his theoretical and experimental investigations on the conduction of electricity by gases. This honor solidified his reputation as one of the leading scientists of his era. He was also knighted in 1908, and in 1912, he was appointed to the prestigious position of Master of Trinity College, Cambridge. His accolades included numerous honorary degrees and memberships in distinguished scientific societies around the world, reflecting the international impact of his work. Despite his immense achievements, Thomson was known for his humility and approachability. Colleagues and students often spoke of his kindness, generosity, and passion for teaching. He believed that the pursuit of scientific knowledge should be grounded in careful observation, experimentation, and a spirit of collaboration. His writings and lectures emphasized the importance of curiosity, patience, and rigor in scientific inquiry. Thomson's dedication to the advancement of science remained steadfast throughout his life, and he continued to be involved in research and teaching well into his later years. As a family man, Thomson enjoyed a quiet personal life. He married Rose Elizabeth Paget in 1890, and together they had 2 children. Their son, George Paget Thomson, would follow in his father's footsteps and eventually become a Nobel Prize-winning physicist himself, recognized for his work on the wave properties of electrons. This continuation of scientific excellence through generations was a testament to the intellectual environment that J.J. Thomson helped to cultivate both at home and in academia. The Thomson household was a place where scientific dialogue and curiosity were encouraged, fostering a legacy that would continue to shape the world of physics long after his time. In the final years of his life, Thomson remained engaged in the academic community, though he gradually reduced his experimental work. The scientific world had evolved rapidly since his early days in the laboratory, but his contributions continued to be acknowledged and celebrated. His name became synonymous with the pioneering spirit of modern physics, a symbol of the transition from classical to atomic and quantum science. As he aged, he witnessed the unfolding of theories and discoveries that had their roots in his own early work, an experience few scientists are privileged to enjoy within their lifetimes. J.J. Thomson passed away on August 30, 1940. At the age of 83, he died peacefully in Cambridge, England, leaving behind a legacy that fundamentally altered the course of human understanding. His passing marked the end of a remarkable chapter in the history of science, but the effects of his work endure to this day. He was buried in Westminster Abbey, close to the graves of other great scientific minds, such as Isaac Newton and Charles Darwin, a fitting honor for a man whose insights had illuminated one of the most profound mysteries of the natural world. Thomson's legacy is not limited to the discovery of the electron alone. He represents the spirit of scientific innovation and perseverance. His story is one of intellect, dedication, and the transformative power of curiosity. Through his work, the invisible components of matter were brought to light, reshaping the way we view the universe at its most fundamental level. Generations of scientists have stood on his shoulders, building on the principles he helped uncover. His name is etched into the history of physics as a symbol of insight and inspiration, a beacon for those who dare to explore the unknown in the pursuit of truth. Even today, in classrooms and laboratories around the world, the influence of J.J. Thomson continues to be felt. Students learn about his cathode ray experiments, the first glimpses into the subatomic world, and the profound implications of discovering the electron. His contributions laid the groundwork for the electronics revolution, nuclear physics, and quantum mechanics. Without his pioneering work, modern technology from computers to medical imaging devices would not exist in its current form. Thomson's life was not just a testament to scientific brilliance, but also to the enduring value of education, curiosity, and the relentless pursuit of knowledge. Warren Schrödinger, one of the foremost figures in the development of quantum mechanics, is renowned for his pivotal contributions to theoretical physics and for proposing one of the most iconic thought experiments in science, Schrödinger's cat. Born on August 12, 1887, in Vienna, Austria, he was raised in a well-educated and intellectually stimulating environment. His father, Rudolf Schrödinger, was a botanist and oilcloth manufacturer, while his mother, Georgine Amelia Brenda, was of part English descent and culturally inclined. From an early age, Schrödinger demonstrated a strong aptitude for science and mathematics, excelling in academic pursuits and developing a deep interest in the natural world. He received his early education through a combination of homeschooling and formal instruction, which provided him with a solid foundation in classical literature, philosophy, and languages, along with the sciences. In 1906, he enrolled at the University of Vienna, where he studied under prominent physicists like Franz S. Exner and Friedrich Hassenhall. During his time at university, Schrödinger was influenced by both rigorous scientific discipline and a philosophical curiosity that would characterize much of his later work. His academic brilliance soon became evident, and he earned his doctorate in physics in 1910. Following his graduation, Schrödinger served as an assistant to Exner and began to make a name for himself in academic circles. He was drafted into the Austro-Hungarian army during World War I and served as an artillery officer on the Italian front. Despite the war, he managed to continue his studies, even engaging in scientific correspondence during his military service. After the war, he held a variety of academic positions across Europe, including brief appointments in Vienna, Jena, Stuttgart, and Breslau. These early professional years were marked by both intellectual growth and a restless search for a stable academic environment. In 1921, Schrödinger accepted a position at the University of Zurich, where he would carry out the work that earned him international recognition. It was here, in 1926, that he formulated the Schrödinger equation, a fundamental result in quantum mechanics. This wave equation provided a way to calculate the behavior of quantum systems and formed the basis of what is now known as wave mechanics. It described how the quantum state of a physical system changes over time and offered a mathematical framework for understanding particles at the atomic and subatomic levels. Schrödinger's approach contrasted with the matrix mechanics developed by Werner Heisenberg. But both theories were eventually found to be equivalent in terms of physical predictions. The Schrödinger equation revolutionized the field of quantum physics and earned him widespread acclaim. In recognition of this groundbreaking work, he was awarded the Nobel Prize in Physics in 1933, which he shared with Paul Dirac. This honor solidified his place among the leading physicists of the 20th century. Schrödinger's contributions extended beyond his famous equation. He also worked on statistical mechanics, general relativity, and color theory, among other subjects. His writings reflect a mind that was both scientifically rigorous and philosophically inquisitive, often delving into the nature of reality and the limits of human understanding. Perhaps the most widely known aspect of Schrödinger's legacy is the thought experiment he proposed in 1935, now known as Schrödinger's cat. This imaginative scenario was designed to illustrate the paradoxes of quantum superposition and the measurement problem. In the thought experiment, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the Geiger counter detects it, triggering the hammer to break the vial and release the poison, killing the cat. According to the quantum mechanical interpretation at the time, until the box is opened and the system observed, the cat is considered to be both alive and dead simultaneously. Schrödinger intended this paradox to highlight the strangeness and counterintuitive nature of quantum mechanics when applied to macroscopic systems. Though originally posed as a critique, the cat paradox became a central topic in discussions about quantum theory and interpretation. In 1933, following the rise of the Nazi regime in Germany, Schrödinger, who had been appointed to a prestigious position at the University of Berlin, chose to leave the country due to his opposition to the regime and his personal situation. He had a complicated private life, including a relationship with a woman other than his wife, which further made life under the strict social codes of the Nazi state untenable. He moved briefly to Oxford, England, where he was offered a fellowship at Magdalen College. However, due to tensions arising from his unconventional personal life, he did not stay long. He eventually moved to the University of Graz in Austria, but political pressures once again forced him to leave. Schrödinger found more permanent refuge in Ireland, where he was invited by Eamon de Valera, then Taoiseach of Ireland, to help establish the Institute for Advanced Studies in Dublin. He accepted the invitation and moved there in 1939. During his time in Dublin, Schrödinger continued to publish scientific papers and gave lectures that were often philosophical in tone. He also wrote What is Life?, a book that explored the relationship between quantum physics and genetics. This influential work inspired later developments in molecular biology and was read by pioneering scientists like Francis Crick and James Watson. Schrödinger's ability to bridge disciplines and inspire new lines of inquiry underscored the breadth of his intellectual vision. His time in Ireland was marked by productivity and stability, though he remained somewhat isolated from the mainstream physics community. In 1956, he returned to Vienna, where he resumed a more subdued academic life. By this time, his health had begun to decline, but he remained mentally active and deeply engaged with philosophical questions about science and reality. His later years were reflective and focused on revisiting the philosophical implications of quantum mechanics, a subject he had long contemplated. He believed that the mysteries of the quantum world raised important questions about the nature of observation, consciousness, and the limits of scientific knowledge. Erwin Schrödinger died on January 4, 1961, in Vienna, at the age of 73, had been suffering from tuberculosis, a condition that he had battled at various points in his life. His death marked the end of a remarkable career that had transformed the landscape of modern physics. He was buried in Alpbach, Austria, a quiet alpine village where he had spent time reflecting and writing. His grave bears a simple inscription, including the famous Schrödinger equation, a lasting symbol of his contribution to science. Schrödinger's legacy endures not only through the formalism of wave mechanics, but also in the philosophical debates his work continues to provoke. His insistence on grappling with the conceptual implications of quantum theory has ensured that his name remains central to discussions about the nature of reality and the role of observation in science. Today, Schrödinger's cat serves as a cultural shorthand for the mysteries and contradictions of quantum physics, appearing in educational contexts, popular media, and scientific literature alike. It represents both the ingenuity of his thought and the profound challenges posed by quantum mechanics. His life, filled with intellectual exploration and personal complexity, reflects the broader story of 20th century physics, a period of immense discovery, upheaval, and philosophical re-evaluation. Schrödinger exemplified the ideal of the scientist-philosopher, someone who pursued truth not just through equations and experiments, but through deep reflection on the meaning behind the data. His work, often bridging science and philosophy, inspired generations of physicists to consider not only how the universe works, but what that knowledge means for our understanding of existence itself. Even decades after his death, Schrödinger's influence remains deeply embedded in modern science. His ideas have helped shape fields as diverse as quantum computing, molecular biology, and theoretical cosmology. As science continues to probe the fundamental nature of reality, the questions Schrödinger raised remain as relevant as ever. His contributions continue to echo in the corridors of research institutions, classrooms, and philosophical debates worldwide, testifying to the enduring power of a curious and disciplined mind. Lise Meitner, an extraordinary physicist whose work significantly shaped modern nuclear science, is best known for her role in the discovery of nuclear fission, one of the most transformative scientific breakthroughs of the 20th century. Born on November 7, 1878, in Vienna, Austria, she was the third of 8 children in a middle-class Jewish family. From a young age, Meitner demonstrated an intense curiosity and aptitude for learning, especially in mathematics and physics. However, growing up in an era when women were largely excluded from higher education, she faced societal constraints that made her scientific aspirations all the more difficult to pursue. Despite these barriers, she persevered with remarkable determination, ultimately carving out a place for herself in a male-dominated scientific world. In her teenage years, she was tutored privately, as girls in Austria were not allowed to attend public universities. After women were finally granted the right to higher education, Meitner enrolled at the University of Vienna in 1901, where she studied under the guidance of the renowned physicist Ludwig Boltzmann. Boltzmann's teachings and enthusiasm for atomic theory deeply inspired her. She earned her doctoral degree in physics in 1906, becoming only the second woman to receive such a distinction from the institution. Her early academic success was a testament to her intellect and determination to contribute meaningfully to science, despite the odds stacked against her. Eager to engage in advanced research, she moved to Berlin in 1907 to study with Max Planck, one of the fathers of quantum theory. Initially, Planck did not accept female students, but he made an exception for Meitner, a decision that would ultimately benefit the future of physics. In Berlin, she began a long and fruitful collaboration with chemist Otto Hahn, who would become her closest research partner for over 3 decades. Due to her gender, Meitner was initially not allowed to work inside the main laboratories of the Kaiser Wilhelm Institute, so she conducted her experiments in a makeshift lab in the basement. Despite such limitations, she remained focused on her work, and soon gained a reputation as an exceptional experimentalist and theoretician. Through the 1910s and 1920s, Meitner and Hahn produced numerous important papers in radioactivity and nuclear chemistry. Their work on radioactive isotopes and the behavior of atomic nuclei placed them at the forefront of nuclear research in Europe. Meitner was instrumental in developing techniques for isolating and identifying radioactive elements, helping to deepen the understanding of atomic transformations. In 1926, she became the first woman in Germany to hold a full professorship in physics, a remarkable achievement that reflected her growing recognition in the scientific community. Her academic and professional status grew, but her contributions were often overshadowed by her male counterparts, a reflection of the era's gender biases. The rise of the Nazi regime in Germany during the 1930s placed Meitner, who was of Jewish heritage, in an increasingly precarious position. Although she had converted to Christianity earlier in her life, Nazi racial laws defined Jewishness by ancestry rather than faith. By 1938, the political situation had become untenable, and she was forced to flee Germany. With the help of Dutch physicists and colleagues in Sweden, she escaped to Stockholm, leaving behind not only her home but also the laboratory where she had worked side by side with Hahn for many years. This sudden exile deeply affected her emotionally, but she quickly resumed her scientific work in Sweden, despite limited resources and institutional support. During this period, Hahn continued experiments in Berlin with Fritz Strassmann to identify the products of neutron bombardment in uranium. They observed results that didn't fit conventional theories of nuclear reactions. Meitner, from her new base in Sweden, remained in contact with Hahn and played a critical role in interpreting these puzzling findings. In December 1938, Meitner, working with her nephew Otto Frisch, provided the theoretical explanation that the uranium nucleus had actually split into two smaller nuclei, a process that released a massive amount of energy. They recognized this as nuclear fission, the splitting of an atomic nucleus, and published their interpretation in early 1939. This was the key to understanding how a chain reaction could be produced, laying the groundwork for both nuclear power and atomic weapons. Despite her pivotal role in explaining nuclear fission, Meitner was overlooked when the Nobel Prize in Chemistry was awarded solely to Otto Hahn in 1944. The decision has been widely criticized in the scientific community and is seen as a glaring omission. Rooted in the sexism and political pressures of the time, Meitner, who had never participated in the creation of atomic weapons, was deeply distressed by the use of nuclear fission in warfare, particularly the devastation caused by the atomic bomb dropped on Hiroshima in 1945. She was offered roles in the Manhattan Project but declined, staying true to her ethical stance that science should serve humanity, not destruction. Although she did not receive the Nobel Prize, Meitner's achievements were eventually recognized in other ways. She received numerous awards later in life, including the Max Planck Medal and the Enrico Fermi Award, and was honored by institutions around the world. Element 109, Meitnerium, was named after her in 1997, a rare recognition that immortalized her legacy in the periodic table. Her contributions were finally receiving the appreciation they deserved, though it came too late to reflect the extent of her original role in the discovery of fission. In her personal life, Meitner remained modest and intellectually driven. She never married and dedicated much of her time to her research and academic pursuits. Despite the hardships of exile and professional neglect, she maintained her dignity and continued to advocate for women in science and ethical responsibility. In research, her resilience in the face of discrimination and adversity serves as an enduring example of integrity and perseverance. She also emphasized collaboration and mentorship, helping younger scientists and encouraging critical thinking and moral reflection. In scientific work in her later years, Meitner retired from active research but remained engaged with the scientific world. She spent her final years in the United Kingdom, living in Cambridge with her nephew Otto Frisch, and continuing to write and speak about science. Though age and health gradually diminished her physical activity, her mind remained sharp, and she stayed informed on scientific developments well into her 80s. Her legacy grew as the post-war scientific community re-evaluated her contributions and recognized the critical role she had played in the foundations of nuclear physics. Lise passed away on October 27, 1968, just shy of her 90th birthday. She died peacefully in Cambridge and was buried in Bramley, Hampshire, England. Her grave bears an epitaph written by her nephew, a physicist who never lost her humanity. These words encapsulate the essence of Meitner's life. A scientist who never allowed ambition to override her moral compass. Her passing marked the end of a remarkable journey through some of the most turbulent and transformative times in modern history. The story of Lise Meitner stands as a powerful reminder of the importance of scientific integrity, the value of perseverance, and the enduring impact of unsung heroes in the world of discovery. Her work not only changed the course of science, but also inspired future generations to challenge injustice and pursue truth. No matter the obstacles, Meitner's contributions to physics, long overlooked by history, are now firmly recognized as foundational, and her name is forever linked with one of the greatest scientific discoveries of all time. Her life and work exemplify the profound potential of the human spirit when guided by intellect, courage, and compassion. Hans Bethe, a towering figure in 20th century physics, left an indelible mark on the scientific world through his pioneering work in nuclear physics, astrophysics, and his crucial role in the Manhattan Project. Born on July 2, 1906, in Strasbourg, then part of the German Empire, Bethe grew up in a family that valued education and intellectual achievement. His father was a physiologist, and his mother was a musician and writer, both of whom instilled in him a strong appreciation for academic pursuits. From a young age, Bethe displayed a profound interest in mathematics and science, showing the kind of intellectual discipline and curiosity that would later define his career. He pursued his early education in Frankfurt, Germany, where he excelled in school and went on to study at the University of Frankfurt before transferring to the University of Munich. There, he studied under the influential physicist Arnold Sommerfeld, who had mentored many prominent scientists of the era. Bethe completed his doctoral degree in theoretical physics in 1928 at the age of 22, focusing on electron interactions and solid-state theory. His academic brilliance quickly garnered attention, and he began to develop a reputation as a rising star in European physics circles. Early in his career, he worked at several prestigious institutions, including universities in Stuttgart and Leipzig. During the early 1930s, Bethe published important research in quantum mechanics, physics, and atomic theory. He made significant strides in understanding nuclear reactions, laying the foundation for future developments in nuclear energy. His early work also involved writing review papers that synthesized vast areas of knowledge in the emerging field of nuclear physics, earning him recognition for both his scientific insights and his clarity of thought. However, the rise of the Nazi regime in Germany drastically altered the trajectory of his life. Being of Jewish heritage on his mother's side, Bethe faced discrimination under the new racial laws, and in 1933, he was dismissed from his academic post. Forced to leave Germany, Bethe emigrated first to England, and then in 1935, he accepted a position at Cornell University in the United States. There, he found a welcoming academic environment that allowed him to flourish. He became a central figure in American physics, contributing extensively to nuclear theory and mentoring many students who had become distinguished scientists themselves. His work during the late 1930s included breakthrough research in astrophysics, particularly his explanation of how stars produce energy. In 1938, he published a paper describing the proton-proton chain reaction and the carbon-nitrogen-oxygen cycle to processes that powered the Sun and other stars. This work earned him the Nobel Prize in Physics in 1967 and remains a cornerstone of modern astrophysics. As World War II intensified, Bethe was called upon to lend his expertise to national defense. In 1942, he joined the secretive Manhattan Project, the United States' top-secret program to develop the first atomic bomb. Bethe served as the head of the theoretical division at Los Alamos Laboratory in New Mexico. His leadership was instrumental in solving complex physics problems related to bomb design, particularly those involving the implosion mechanism for the plutonium bomb. He played a central role in ensuring the weapon's effectiveness, guiding calculations and theoretical models that underpinned its construction. Bethe was known for his ability to communicate intricate scientific concepts with clarity and authority, which helped unify the efforts of scientists from diverse backgrounds working on the project. Despite his critical contributions to the atomic bomb, Bethe was deeply conflicted about its use. After witnessing the devastation of Hiroshima and Nagasaki, he became an advocate for arms control and nuclear non-proliferation. He supported the international regulation of nuclear weapons and worked tirelessly to promote responsible scientific research in the post-war world. Bethe remained active in scientific advisory roles to the U.S. government, providing guidance on nuclear policy and national security issues. He helped influence decisions on arms treaties and was a vocal supporter of the peaceful use of nuclear energy. Returning to Cornell after the war, Bethe resumed his academic career, teaching and conducting research for the rest of his life. He made significant contributions to a range of disciplines, including quantum electrodynamics, particle physics, and hydrodynamics. He continued to write influential scientific papers well into his later years and remained an active participant in major scientific discussions. His post-war work also involved advising younger scientists, many of whom went on to become leaders in their respective fields. Bethe's ability to adapt to new areas of physics and maintain relevance across multiple decades was a testament to both his intellectual flexibility and enduring passion for science. Bethe's character was marked by humility, integrity, and a commitment to ethical responsibility in science. Colleagues and students often remarked on his generosity, patience, and willingness to help others. Unlike many of his contemporaries, Bethe did not seek the spotlight. Instead, he focused on solving problems, improving the world through knowledge, and mentoring the next generation of scientists. His moral stance against the misuse of scientific discoveries was unwavering, and he consistently advocated for diplomacy and transparency in international science relations. Throughout his life, Bethe received numerous accolades for his contributions to science. In addition to the Nobel Prize, He was awarded the Enrico Fermi Award, the Max Planck Medal, and the National Medal of Science, among many other honors. His membership in scientific academies around the world reflected the global recognition of his work. Despite these achievements, Bethe remained modest, often attributing his success to collaboration and a relentless curiosity about the universe. He believed that science should serve humanity and that its practitioners had a duty to use knowledge wisely and ethically. In his personal life, Bethe was known for his warmth, wit, and affection for family. He married Rose Ewald in 1939, the daughter of another noted physicist, and the couple had 2 children. Their relationship was a stable and supportive one, rooted in mutual respect and shared intellectual interests. Bethe maintained a balanced life, enjoying music, literature, and time with his family, while continuing to pursue his scientific interests with vigor. His ability to harmonize personal and professional commitments made him a respected figure, not only in the scientific community, but also among those who knew him personally. As he aged, Bethe never lost his zeal for learning. Even in his 80s and 90s, he continued to contribute to scientific discussions, publish papers, and attend conferences. His mind remained sharp, and his insights were valued by peers and newcomers alike. He frequently revisited earlier topics in physics, always with a fresh perspective and a desire to deepen understanding. This lifelong dedication to discovery reflected his belief in the power of science as a force for progress and enlightenment. Hans Bethe passed away on March 6, 2005, at the age of 98, in Ithaca, New York. His death marked the end of a remarkable journey that spanned nearly a century of scientific evolution. He died peacefully at home, surrounded by the community he had helped build and the academic institution he had served for decades. His passing was mourned by scientists, students, and policymakers across the world, who recognized the vast contributions he had made not only to physics, but to humanity at large. The legacy of Hans Bethe is one of brilliance, responsibility, and service. His work helped unlock the secrets of the stars, shaped the course of human history during a time of global conflict, and guided the ethical development of nuclear science. His name remains synonymous with both intellectual excellence and moral reflection in the field of physics. Bethe's life story continues to inspire those who seek to understand the natural world and use that knowledge for the betterment of society. Through his discoveries, teachings, and example, Hans Bethe stands as a towering figure in the history of science, a man whose influence will be felt for generations to come. Emmy Noether, one of the most brilliant mathematicians of the 20th century, forever changed the landscape of theoretical physics and mathematics through her groundbreaking work. Most notably Noether's Theorem. Born on March 23, 1882, in Erlangen, Germany, Amalie Emmy Noether was the daughter of Max Noether, a well-known mathematician, and Ida Kaufmann. Raised in an intellectually vibrant household, Emmy initially seemed more inclined toward the arts and languages, yet she soon gravitated toward mathematics, the field in which her father had excelled. Despite the societal barriers for women at the time, she pursued her passion for numbers and logic with extraordinary persistence and courage, charting a path that was as bold as it was brilliant. In an era when academic opportunities for women were severely limited, Emmy Noether faced institutional and cultural challenges that would have discouraged many. At the time, women were largely prohibited from enrolling formally at German universities. Initially, she was only allowed to audit classes at the University of Erlangen, where her father taught, but in 1904, policies changed and she officially enrolled. Her academic performance was exceptional, and she later moved to the University of Göttingen, where she completed a dissertation under Paul Gordon in 1907. Though the thesis was modest by her later standards, it marked the beginning of a career that would reshape modern mathematics and physics. Her mind, even then, displayed the unique depth of abstraction and elegance that would define her later achievements. After earning her doctorate, Noether returned to Erlangen and spent the next several years conducting research and teaching without pay or title, as women were still not granted formal academic positions in many institutions. During this time, she began developing ideas in abstract algebra, a field that was evolving rapidly. Her work contributed to the structural approach to algebra that emphasized general principles over specific calculations. She was eventually invited back to Göttingen in 1915 by the esteemed mathematicians David Hilbert and Felix Klein, who recognized her extraordinary talent. Even so, due to prevailing sexism, She was not allowed to lecture under her own name, and instead did so under Hilbert's. Hilbert famously defended her presence in the faculty with the sharp remark that the faculty was not a public bathhouse, where gender should be an issue. In Göttingen, Noether flourished intellectually. Her 1918 publication, which introduced what became known as Noether's Theorem, stands as one of the most profound contributions to theoretical physics. The theorem elegantly connected symmetries in physical systems to conservation laws, establishing a foundational principle that lies at the heart of modern physics. For example, the symmetry of time leads to the conservation of energy, while the symmetry of space results in the conservation of momentum. This theorem provided a critical mathematical framework for the development of Einstein's general theory of relativity, and later became a cornerstone in the field of quantum mechanics. The brilliance of this result lies not only in its mathematical sophistication but in its unifying power, revealing a deep connection between the form and laws of the physical universe. Noether continued her research with boundless energy, contributing extensively to ring theory, group theory, and module theory. Her work was often years ahead of her time, emphasizing abstraction and generalization at a level that would only be fully appreciated decades later. Her algebraic innovations provided a new language and framework that transformed the field from a collection of techniques into a coherent, deeply structured discipline. She trained and influenced a generation of mathematicians, many of whom would carry her insights into the wider world of science. Though her teaching style was informal, it was deeply engaging, and students were drawn to her warmth, clarity, and intellectual rigor. She encouraged independence of thought and fostered a community of inquiry that became known as the Noether School. Despite her unmatched intellect and growing influence, Noether remained without a full professorship for most of her career. The academic world was slow to recognize her due to entrenched biases, and she worked tirelessly in an environment where her achievements were not always met with the honors they deserved. Nevertheless, she remained focused and optimistic, caring more for the advancement of ideas than for accolades. Her personality was characterized by modesty, generosity, and an unwavering dedication to truth and knowledge. She led a simple life, uninterested in material possessions or personal fame, and was known for her humor and kindness among her students and colleagues. The rise of the Nazi regime in 1933 brought a devastating turn to her career and life. As a Jewish woman in academia, Noether was dismissed from her teaching position at Göttingen. The university lost one of its brightest minds due to political persecution. Forced into exile, she accepted a visiting professorship at Bryn Mawr College in Pennsylvania, United States. There, she found a welcoming academic community and a renewed opportunity to teach and conduct research. She also lectured at the Institute for Advanced Study in Princeton, where leading scientists, including Albert Einstein, acknowledged her intellectual prominence. Though her time in America was brief, it was a period of great productivity and influence. She played a pivotal role in introducing modern algebra to the American academic world, and her reputation continued to grow among mathematicians across the globe. Tragically, her time in the United States was cut short. In April 1935, Emmy Noether underwent surgery to remove a uterine tumor. Though the operation initially seemed successful, she died unexpectedly 4 days later. On April 14, 1935, due to complications. She was 53 years old at the time of her death, and the scientific community mourned the loss of a mind whose depth and clarity had few equals. Einstein, in a letter to the New York Times, praised her as a creative mathematical genius and lamented that she had not been given the recognition she deserved during her lifetime. Her passing marked not only the end of an individual life, but the loss of a profound intellect, whose ideas had only just begun to take root in the wider scientific world. In the years following her death, Emmy Noether's influence grew steadily. Her ideas reshaped both mathematics and theoretical physics, guiding countless researchers and forming the backbone of major developments in modern science. The full significance of her work was gradually acknowledged, and today her name is honored in the highest circles of academic thought. Schools, mathematical concepts, and lectureships have been named after her. Her theorem remains one of the most important tools in understanding the principles of nature, used across fields from particle physics to cosmology. Her approach to abstract reasoning and structural thinking continues to shape contemporary mathematical education and research. Life stands as a testament to intellectual courage, resilience, and the relentless pursuit of truth in the face of adversity. She broke through barriers not only of mathematics but of societal limitations, showing that true genius cannot be confined by prejudice. Emmy Noether's legacy transcends her gender and her era. She opened doors that had long been closed to women in science and mathematics, and by the strength of her work alone, she earned a place among the most influential thinkers in history. Her contributions remain as vital today as they were revolutionary in her time, serving as both a foundation and a beacon for future generations of scientists and mathematicians. Her story continues to inspire those who face obstacles in pursuit of their calling, proving that brilliance, when combined with persistence and integrity, can change the world.